Special diodes. We will see different special diodes and their characteristics and applications and how it is really developed from the basic diode called junction diode. The list of the diodes I mentioned here: Junction Diode, Zener Diode, Avalanche Diode, Kernel Diode, Indium and Phosphorus, Gallium arsenide, mass diode, photodiode, light emitting diode called LED, varactor diode, laser diode, solar diode and Schottky diode. All these diodes we will briefly see to understand their applications. First we will start with classification of diodes. Diodes I have classified as based on doping and others are special diodes. In doping, junction diode, Zener has more, Avalanche has still more doping, Kernel has much more, Indium phosphorus has much more, Gallium arsenide is the highest. So as the doping is increasing this side, breakdown is increasing this side. That means these diodes will have less background voltages, and that is the meaning of this table. You can see increase of doping this side, increase of breakdown. Therefore I have a saying, as doping increase, breakdown decrease. Let's see the different characteristics. Suppose forward bias is almost the same silicon diode. For silicon diode, as we already studied, this is breakdown, spoiling. Spoiling means what? Dotted line. As doping increased, as I told you, this is slowly decreasing. Therefore, this is spoiled, these are not spoiled. But these two are useful for breakdown, these three are almost less. That's why reverse characteristics I try to put on the single graph. Then first diode, junction diode. Though we have studied so much on this, but as slight conclusions, it's a lightly doped, equally doped, linear graded, grown type. Junction voltage is given as Vj alpha W cube by 12 epsilon, where rho V is alpha x. Capacitance is given by Ct is epsilon A by W. The specifications of a junction diode also we saw. This I have given just for a reference, and Ni, intrinsic carrier concentration, mobility of electron, mobility of hole, rho V charge density, resistivity, energy gap, cut-in voltage, I0, Ni and all this. So this is the comparison of junction diode. Every diode has arrow, but the diode itself is an arrow. Normally every device you will put arrow, but in a junction diode that itself is arrow. But what is arrow shows? Arrow shows conventional current direction when the junction is forward biased. Suppose if you forward bias junction, current flows in this direction, that's why it is the current direction. Applications of PN diode. It is used as a switch, it is used as a clipper and clampers, and used for non-linear applications such as modulators. That's about first diode. Now I am taking you for second diode, Zener diode. It is heavily doped device. It is made up of silicon, as in fact by default all the devices are made up of silicon. What I mean, if it is not mentioned, it is by default taken as made up of silicon. In forward direction it is same as silicon diode, but in reverse direction it has so many effects, and the temperature is change, range is more, and it is cheaper. Now let me explain reverse bias concept. Suppose Vz is 7.2 volts. At low voltage means 0 to 4, this voltage develops current called Zener effect. That's called primary emission. Zener effect is generally due to voltage. At medium, if the voltage increases continuously, carriers collide and produce a big current called secondary, and that is called avalanche effect. Therefore, in the medium range, you have both Zener and avalanche. Zener effect is continuing and avalanche affecting is initiated. But at high voltage, like of course more than 6 volt in this example if I take, it is increasing and avalanche is dominating the Zener effect. So finally secondary current will increase. That's how characteristics come. I just tried to explain the difference between Zener effect and avalanche effect, because most of the time the question papers are asking, well, first point, it is due to breaking of the bonds, whereas avalanche, it is due to collisions. Whatever breaking is done, and out of that carriers come, and that carriers will really become collisions there. And Zener effect is due to electric field, whereas avalanche effect is due to temperature. And Zener effect is primary emission and avalanche effect is secondary emission. In Zener effect the current is small and avalanche effect current is large. It is observed below breakdown and that's observed after breakdown. This is how I tried my level best to really compare and make you and see that you will really follow the questions well. And the symbol for this is same as junction diode. Please remember this line is junction, but Z is for Zener. Applications of Zener. As doping increase, breakdown decrease, and hence the devices are safe and it's used as a regulator. Actually in speaking, generally people say Zener is acting as a regulator in reverse direction. But the reality is, even in the forward, it can be used as a regulator. For example, when you see forward direction, at the saturation it is 0.8 volts. So it can be used as a breakdown even in the forward direction. But silicon can do the job, therefore silicon is cheaper and hence people don't use Zener in the place of silicon. But when you go to reverse bias, in the reverse bias silicon junction diodes will not be used, whereas Zener only can work because they don't spoil. So silicon and Zener is not used because of the breakdown and it will physically spoils there. Therefore we don't use it. Let's go to third diode. Third diode we call it as avalanche diode. That is, as doping is further increased, avalanche is observed earlier. See, very simply speaking, as the doping is increasing, when the collisions increase, the secondary emission starts little earlier. It is more doping than Zener. It breaks at less voltage. Zener and avalanche is used as regulators. Zener is not a switch. You know why Zener is not a switch? Because forward direction it has a current, reverse direction also it has a current. Strictly speaking, in the reverse direction there is some place where you can use it as a switch because below breakdown it has almost zero. So but generally it cannot be used as a switch. It is not preferred as a switch because silicon is cheaper than Zener. So coming to switch, silicon junction diode is good, and regulator Zener and avalanche is good. So if IR is less than IZ minimum, diode acts as an off switch. If you see IZ minimum, it acts as a, that means if the breakdown not started, it is at off switch. After breakdown, it can act as an on switch even in the forward direction. So ultimately, Zener and avalanche can be used as regulator. The good thing is they give a constant voltage without spoiling it physically. Please remember, junction diode in breakdown it physically spoils. Zener diode, it doesn't spoil physically. That's why it can work. This is the reason why people generally call it as Zener and avalanche is called as regulated diodes. Now I'm just showing IV characteristics. Some people call IV, some people call VI, it doesn't matter. IV characteristics here. This is the as temperature is there, and this also as temperature is there. So this is basically room temperature. There is a forward and in the reverse. So you can use it as a regulator both in the forward and reverse, but in the forward, after all, very less voltage. But why should we use Zener, which is costly? You can use a junction diode instead. So that's why it's so popular. In the forward, silicon diode, junction diode, whereas in Zener, silicon diode. Zener is made up of silicon because it has a large temperature range and it is cheap. Applications. Avalanche diodes are used to protect circuits against surges, lightning and other transients. So if there is any transient to be avoided, you can use this. They are faster than Zeners and gas tubes. Avalanches are used as a substitute for high voltage circuits due to pulses. It is used to improve voltage ratings. So this is application of Zener. Now I am taking you to tunnel diode. It works always in forward bias. It has a narrow depreciation. You know why always actually? Because as I told you, as doping is increasing, breakdown is decreasing, it's almost zero. So more popular in the forward. Gallium arsenide material used, it can be exit a negative resistance region. And the symbol is given like a tunnel. Symbol is used like a tunnel. And IV characteristics of a tunnel diode. Look at here, this is going on increasing. Actually it's supposed to go further. If it is lightly doping, it goes further. But because doping is increased, it comes down because of collisions. And that becomes, it goes on down till there is no collisions, and that's called valley voltage and valley current. And once the collisions are avoided, it goes on increasing again. So this is called valley voltage, valley current. This is called valley peak voltage and peak current. In this region, it is acting as negative resistance region. So these operations are very simple, and it's negative resistance region applications. It has a heavily doped than Zener and silicon, Avalanche. Reverse voltage neglected, forward bias characteristics, initial current is increasing and then further increase. Because of the collisions, it gets decreased, and that's called negative resistance region. Once collisions are eliminated, current increases once again. As current decreasing, we call it as tunneling phenomenon. In negative resistance region, it acts as a bilateral switch. It is used as a blocking oscillator. It has a high speed applications. So this is the meaning of what you call tunnel diode. What are the applications? Because it has a negative resistance region, it is used as a blocking oscillator. It is used as a fast tester switch, used for microwaves and microwave devices. The drawback is self-oscillating. How do you say it is self-oscillating? If you see the internal diagram, equivalent diagram, you have a inductor, resistor, capacitor and resistor. So once you have L and C, and they will have a self-oscillating concept. When you are trying to tune somewhere, they themselves will be tuned. That's the meaning of self-oscillating is a drawback. Then fifth one, indium phosphorus. It has a heavier doping than tunnel. Then VRB is less, and it is faster than tunnel diode. Used in microwave devices, the gun effect is used at higher frequency, more than 1 giga. When you say more than 1 giga, it's normally microwave devices. In fact, if the same concept like a tunnel appears, but this occurs earlier, because as doping increases, the tunneling behaving affects earlier. So it is just like a peak and valley and negative resistance region, but it occurs earlier. For example, if tunnel voltage occurs at 5, when phosphorus occurs at 3 and gallium occurs at 2, the further decreased. That's its meaning of the characteristics. And what are they? They are used in microwave frequencies. They are called gun diode. They are used in microwave oscillators. So this is the special diode we have. Sixth one, gallium and arsenide. That's faster than indium phosphorus, heavier than indium phosphorus. Breakdown voltage or reverse voltage almost neglected. VP is also lesser, IV is lesser. It's the costliest of all and the fastest of all. Even today in VLSI, one of the greatest material that we are using is gallium arsenide, and it became the fastest of all and costliest of all. And it has a property of gun effect, and hence it is used in microwave device. There is a schematic symbol, N-type gallium arsenide, and metal here. This is the meaning of what you call your gallium arsenide diode. Let me just tell one word about gun effect. Above some critical voltage corresponding to a field of 2K, 4K, 2000 or 4000 volts per centimeter, and that means, please understand, it is a field effect. Electric field is always called volts per centimeter. The current passing through N-type germanium gallium arsenide becomes a periodic fluctuating function of time. When it is happening periodic fluctuating function of time, we call it as gun effect. The frequency of oscillation is determined mainly by the specimen, not by the external circuit. Period of oscillation is inversely proportional and the specimen length is equal to the transient time of the electrodes. This is what it means by the gun effect here. Then advantages. What are the advantages we have in this gun diode? It has higher saturated electron velocity. It has a direct band gap. It's used in mobile phones, satellite communication, used in manufacturing of gun diode for generation of microwave devices. So these are the under the gun diodes. So far we have finished something based on what you call doping. Now I am taking a different special things, much more special. They are based on what you call mass diodes. Mass diode, look at here, this is a semiconductor. These two are two metals, this metal and a semiconductor here. And forward bias and reverse bias almost same, because first of all it has only a n type and one way, there is no junction between them. We can say majority carriers only flow. It's obtained for semiconductor and metal, because this is a semiconductor, this is a metal. So this is called metal oxide semiconductor diode. Cut-in voltage is generally decreased. You can use silicon material here. The rectifier applications, that too at high frequency it is used. And as the cut-in voltage is lesser, you can prefer this is better rectifier. That's a mass diode. If you see, I'll show you, this is an ordinary voltage, bilateral signal. If you use silicon 0.6, if you use any junction, you see it has junction rectifier above 0.6 it does, and even in the negative also it works. Some people say in negative there is no current. That's not correct, because in negative there is a reverse current, and if reverse current is multiplied you can have capacitance comes into picture. At high frequency this also exists. There are two problems in junction diode as a capacitor. One is cut-in voltage, up to 0.6 there is nothing. Second is at high frequency internal capacitor comes into picture, and then there is a conduction even in high frequency. Even in negative cycle it comes. Therefore, how to solve these two problems? You can solve them by mass diodes and Schottky diodes, because at high frequency or low frequency, because there is only one. It doesn't work at the frequency, because in the minority carriers, when the diode is off, there is a current generally. Reverse current is there in junction diode, but in mass diode there is no reverse current. When there is no reverse current, automatically conduction is 0. So high frequency you can use them, but generally ordinary diode you cannot use. Normally in the labs when you see at low frequency, that's why you don't see the conduction in the reverse direction. But if you see at high frequency, junction capacitance comes into picture, and accordingly conduction comes into picture. Therefore, you cannot use it as a rectifier, whereas mass diode is good to use because cut-in voltage is less, as well as not even the high frequency. Capacitance may be there, but I naught is not there, it doesn't conduct. So eighth diode, photodiode. Emission is due to light, but collection is by potential difference. Please remember, in any emission, there may be any source of emission, but the potential collection of the current is always by potential difference. So potential difference will give you collection. So if you see that, if you see here, you are giving light here, therefore ID is function of this, function of the intensity, and also function of voltage. So when the intensity of light is also there, we call it as working. So this is light is given and current is flowing. Please understand, this light will give the emission, but collection purpose we have used what you call ID. So when you look at the equation, I is equal to ID dark current, I naught into e power minus 1. This is general current. I'll show you the equation here. This is dark current and this is the I naught into 1 minus E by V power Vt. Applications. It is used in a digital cameras. It is used in medical as well as a blood particle analyzer and X-ray detections. It is used as a safety equipment, as a security inspection equipment, airport X-rays also. So photodiode can detect what is happening inside. So in airports also you can use it. This is the meaning of the diode called photodiode. LED. Emission is by electric field, high loss immunity, cheapest of all, and low power consumes. That's why most of the time people use LEDs for the purpose of indicators. Even if in the bedrooms they have, even for a charger they use LED because they consume less power. These are the curves we have, different colors we have. Advantages. Always used in forward, it has a spontaneous emission, highest lifetime 10 power 6, though 10 power 6 hours is heavy. Even generations it doesn't spoil. Highest noise immunity, it is cheap. Color of LED depends on material used. Depending on the material, the color comes. Applications. It is used for lower display, power displays. It is used in sustaining lightnings and indicator signs. That is already there. You must be seeing in your homes day to day, everywhere LED is there. Next, diode. Varactor diode. It is also called as a voltage variable capacitance or tuning. See, actually whatever I have discussed in junction diode, in reverse bias, abrupt junction, all are valid here. This is the application of varactor. So it is nothing but a junction diode, and hence it is lightly doped, but it is basically what? It is basically step graded junction. And if you see how this is working with temperature, this is the temperature coefficient. And we all know these equations like I have derived. Vj is Q and D by 2 epsilon, epsilon A by W. These are the equations for junction voltage and junction capacitance. Applications. It is used electrically controllable capacitor. It's used in IC fabrications because wherever you want a capacitor you can use it. It has a lot of variations electrically. Laser diode. Laser means light amplification by stimulated emission of radiation. Laser. It is having a direct band gap material. It has stimulated emission. It works on the population inversion principle. Laser diodes are very, very small. So in fact, if they work with radiation, excellent. And this is how you can see light is emitted, depletion layer is here, partially reflective end there, highly reflective end. This is PN diode, laser. Applications of laser diode. They are used in range of finders because in radars we can use. They are used in barcode readers. Suppose you have a barcode in so many libraries and so many things, even in what you call shopping malls. You can just put your code there, it will detect this and the price will come. Widely used in telecommunications. Red lasers are used in CD-ROMs and CD players and DVDs. So lasers, diodes are also used. 12th one, solar cell. Solar is as solar energy is becoming very serious now, so solar cell also we have. It is always used in forward. It works on the photovoltaic principle. That means when you give voltage, photo light, it will convert into voltage and works out. And selenium and silicons are the most widely used material for solar. Current equation is Is into exponential QVT by Vt minus 1 I photon, where IPH is equal to QAG LH plus LG. This is current direction, reverse current is this, forward current is this, solar is given here. So this is called solar cell. And when you see the voltage here and current, This is how it works with the principle of voltage and current. So solar cell is also one of the special diodes we can use. Solar cells are composed of various semiconductor material. Semiconductor become electrically conductive when supplied with light on it. And over 95% of all the solar cells are composed of silicon. If you see the equivalent circuit, this is the equivalent circuit. Shunt resistor, series resistor, current source and a diode. Applications: used in orbital satellites, watches and calculators. Used in portable power supplies, solar. And then Schottky diode, we call it as hot carrier diode. It is referred as Schottky barrier or surface barrier or hot carrier barrier. The ideal diode here along with the capacitor, that's called Schottky. If you draw the equivalent, this is the equivalent, look at it. It will really feel like, if you see this portion, it is just like tunnel diode principle. Because tunnel also have the same equivalent diagram, LP, series inductor, series resistor, parallel inductor, capacitor, parallel resistor. And our Schottky diode characteristics is here. And symbol is S. Instead of Z, we have to put symbol. So let us not confuse with Z and S. S is for Schottky diode. Applications: used in RF mixer and power detector. They are used in high power applications such as power rectifiers. They are used as a clamping diode in transistor circuit to speed the operation when they are used as a switch. Since they are having high reverse leakage currents, they can lead a problem of sensing circuit. They can lead a problem of sensing circuit. How to sense? Illustrative examples. We need to see some problems. Worked out examples. In a Zener diode, only P region is heavily doped, only N region is heavily doped. Both P and N regions are heavily doped. Both P and N are lightly doped. See, one thing we understand in Zener diode, heavy doping is there, but the question comes, both are or 1-1. So if Zener is heavily doped, D cannot be the answer. So the best answer is both are heavily doped, and the option is C. C is the option. Question number 2. A Zener diode works on the principle of tunneling of charge carriers across the junction, thermionic emission, diffusion of charge carriers across the junction, hopping of charge carriers across the junction. That's given in gate. Look at here. Solution. Zener diode works on the principle of tunneling of charge carriers across the junction, which leads junction breakdown, and that is A. If you compare your A, when you look at here, this is A. Therefore, option is A. Question number 3. Choose a proper substitute for X and Y to make the following statement correct. Tunnel diode, correct tunnel diode, and avalanche photodiode are operated in bias, X bias, Y bias respectively. So both are reverse, reverse and forward, forward and reverse, forward and forward. This is also given in gate exam. By that you can understand how special diodes are asked in the exam. Tunnel diodes operated in forward and avalanche diode operates in reverse. So one is forward, other is reverse. The option is C. One is forward, other is reverse. If you see that, this is the option, forward and reverse. Match items groups in 1 with groups in 2. Most suitable group: LED, avalanche photodiode, tunnel diode, laser. Heavy doping, coherent, spontaneous emission, current emission. As I've been telling in matching, I will really take 1 or 2 things which we know. Okay. So when we really see what are the different emissions we have, LED, tunnel diode is basically heavy doping. Laser is a current gain because amplification. So with that, I am giving you the correct option. LED is spontaneous emission. Avalanche photodiode is current gain there, and tunnel diode is heavy doping, and laser is coherent radiation, and therefore the option is C. Heavy doping we can manage, spontaneous with these two at least you can finish off. In a matching, whenever you don't really get all the things known, you can manage with one or at least two things known. So option is C. Group 1 lists for 4 types of PN junction diodes. Match each device in group 1 with one of the options group. Group 2 indicates the bias condition of that device in normal mode of operation. So Zener diode, solar cell, laser and avalanche, forward and reverse. Please remember, most of the diodes in general are by default reverse bias. So this also asked in GATE exam for 2 marks. Look at here, Zener reverse bias, solar reverse bias, laser reverse bias, avalanche also reverse bias. We know avalanche effect is generally in reverse. So most of the diodes in reverse bias. This is the option. Option is B. Question number 6. Match the first one type of diode with the applications in second. Kernel Diode, Zener Diode, photodiode, Schottky diode. These are the diodes, and this is given in IES EEE. And EEE students should understand they are asking all these diodes. So please understand, in IES they are asking. Now let me give you all these options. Kernel Diode exhibits negative resistance region in current characteristics and voltage characteristics. Zener Diode, silicon junction designed for limiting voltage across the reverse bias. That means breakdown. Photodiode, reverse current directly across with light. Schottky diode uses only majority carriers and intended for high frequency operations. So this is what we mean by Kernel Diode, Schottky diodes. Therefore option is C. Match IV characteristics for a given below gun diode, photodiode, Kernel diode. So gun diode is there, photodiode, Kernel diode. What are the matching? Kernel diode we all know, negative resistance region. Then gun diode is almost the same principle, but photodiode is different. So this is also asked for EEE students in IES, so be careful to understand. And gun diode, as I told you, gun diode and Kernel diode almost the same principles, but photodiode is here. That's how you can identify the solution, and then the option is C. C is the option here. Problem 8. Match the list with list 2 properly. Devices and the property. Silicon device, germanium diode, LED pin diode. Silicon diode, and at least 2 diodes if you know, you can make it. Silicon diode has a very low reverse bias saturation current. You know that? Because in silicon, reverse current is nanoamperes. And germanium diode has low bias voltage because that is 0.1. LED has a cutoff wavelength because the wavelength, it depends on light. Pin diode acts as a high frequency applications. So these are the matchings possible. Therefore option is D. D is the option. Question number 9. Match the list with list 2 and select the correct answers. Gun diode, solar, MOSFET, SCR. Gun diode, solar, MOSFET, SCR. Gun diode is a junctionless device. Solar is a single junction device. MOSFET, double junction device. SCR, triple junction device. So the option is A. So in the matching, we have to go for the option. 10th question. The efficiency of an LED for generating light is directly proportional to applied voltage, current injected, temperature, level of doping. Look at the solution. The efficiency of LED for generating light is directly proportional to applied voltage. That is A. Option is A. So we look at the options there. That is option A. We will see illustrative problems, illustrative examples And first question is linked question. For the circuit shown in figure, VZ1 and VZ2 are 100 volts. I01 is 25 micro, I02 is 50 micro, and the voltage given is 90. We have to calculate the current of each diode and voltage across each diode. So that's the problem given, and I call it as a linked problem because the answer for the first one will go as a data for the second one. Let's take this problem. The circuit goes like this. Here is a diode, another diode, Zener diodes. Okay. The voltage given is 90. Say this is diode 1, diode 2. Okay. Now what happens is, he said VZ1, VZ2 100 volts, I01 is 25 micro, I02 is 50 micro. Okay. This is question number 1, as well question number 2. Why 2 questions? These two are linked here, linked there. Then first solution we will go to question number, illustrative question number 1. What is that we wanted? Currents. Current is generally in the direction of diode, and reverse current is opposite. Reverse current is opposite. Forward current, reverse current, forward current, reverse current. Now, the voltage across diode is like this. There is a standard saying, this is positive, negative, positive. Anode is generally taken as positive, and this is given negative. So what do you mean? Each one we have to write. For example, diode 1, this is illustrative question number 1. This is not I1, it is question number 1. Now when you look at the diode 1, reverse bias. Diode 2 also reverse bias. In Zener diode, we need to say simple reverse bias is not sufficient. You need to tell whether it is completely reverse bias breakdown or not. It cannot break because you are giving 100, you need 100, you are giving only 90. Does not break, does not break. Does not break means this is I01, this is I02. This is 25 micro, this is 25, 50 micro. Now which one will flow? You cannot have two things. Two currents cannot flow here. In series, single current flows, which is the least one. This is least one. So answer is 25 microamperes. Then what is that 25? Which direction it is going? You see, this is I01 is finalized. So which direction is this? This is moving this way. That means clockwise. It's simply going in the clockwise direction. Not only clockwise, we need to tell the answers also. I1 is opposite, minus I01, that means minus 25. I2 is minus I02, that means minus 25 again. In both places it is 25. So 25 in this here, also here, two things. I1 is I01, I2 also I01. This is I01 25, this is also I01 25. 25 is going in the clockwise direction. That's the first answer. Now coming to second answer, solution for second problem. I call it as second problem because you have to calculate voltages I2. In that, what is the general expression for current? I is equal to I0 into e power V by eta Vt minus 1. From there, V is eta Vt ln 1 plus I1 by I01. Now please substitute there. Eta Vt ln 1 plus. What is I1? Minus I01 by I01. This is eta Vt ln 0, undefined. And V2 is eta Vt ln 1 plus I2 by I02. What is that? Eta Vt ln minus I01 by I02. Okay. Now substitute what is I01 and I, because in the place of I2 I should write I02. In the place of I2 I01. In the place of I1 also I01. That is the data that I have taken and substituted there. That's why this problem is called linked problem. And in the process, this is 25, 50. So you will get it as Zener is silicon. So 2 into 26 ln 1 minus half. That answer is minus 3.6 volts. If you substitute and calculate, you will get this value. 20 by 50 is half. Then how to calculate V1? V1 will come as KVL V minus 0.360. What is V? 90. So 90 minus 0.36 is the answer. And please appreciate one idea here. This negative takes reverse bias. This negative also say reverse. Whenever the voltage becomes negative, the diode is reverse bias. That's a problem. Linked example for understanding how to calculate current through each diode and voltage across each diode. Question number I3. I for illustration, 3 for 3. Repeat above problem for the supply voltage of 110 volts. What is above problem? There is a diode here, Zener diode. Okay. This is voltage. 110 is given. And let us say D1, D2, V2, V1. I2, I1, I01, I01, I02. Okay. This is plus minus, plus minus, plus minus. VZ1 is VZ2 is 100. I01 is 25. I02 is 50. This is the question given to us. And how do we solve here? Solution. Diode 1, diode 2. Please remember the difference between the problem and previous problem. Previous problem I gave, they gave 90, but now I am giving 110. If I give 110, that means I am giving more than required for breakdown. Now this is true, reverse bias is true, reverse bias is true. But will it break down? Yes. 100 is required, 110 is given, breakdown. But the question is, both of them will break down or one of them break down? For the both of them to break down, you should give 200 volts. But you are giving only 100 there. Therefore, you have to think which one will break first. The reality is this. For example, you have a Zener diode like this, another Zener is like this. This is breaking at 25 micro, this is breaking at 50 micro, and both the voltages are same. When the voltages are same, currents are different, and finally what happens? By the time the current increases to 25, this will break, and that will take the total voltage 100, and remaining is 10. 10 is not sufficient for the breaking of 2. Therefore, this breaks, this does not break. And therefore, I said one sentence, you need to remember this diode with least current break first. Which one will break first? Diode with least current break first. And therefore, once this is breaking, maximum current flows. And once this is not breaking, and therefore, this still have only I02. Whatever the breaking down will have a large current, whatever is not breaking down will have less current. This is less current, therefore overall is what? In series, as I told you, the least one flows. Therefore, now the current is I02. So, if I have to tell the currents now, I1 is equal to minus I02, that is minus 50. I2 is also minus I02 minus 50. Therefore, the circuit currents are 50 micro, but which direction? Same, we are going in the same direction, clockwise direction. Clockwise. Now, currents I have achieved. I need to tell about voltages. V1 is equal to directly 100, V2 is minus 10, and the total is minus 110. Why V1 is 100? Once this is breaking down, it will take 100 volts and the remaining will come here. Therefore, the voltage across first diode is minus 100, second diode is minus 10, and currents are, both of them are minus 50 and 50. That's why I said repeat the above problem doing all these things when the supply voltage increases. When the supply voltage increases, automatically you will have more. Easy to do it because anything breaking down will have large current and therefore least current flows here. This is the approach.